All right, so today we're going to talk about inverse derivatives. Tomorrow we're going to talk about inverse trig derivatives. So the first thing I'd like you to do is at your table, put your heads together and come up with what you know about inverses. Algebraically, like if you have an equation, graphically, you have a graph, numerically, you just have a table of x, y values. What do you know about finding an inverse? Nothing is not true. All right, pod 6. Pick one and tell me about it.
Algebraically.
What do you know?
You have to switch the x and the y, and you have to solve for y.
Okay. Give me a timeout here. All right. Pod 2.
Let's cross the line y equals x.
Okay, graphically, we see that it reflects about the line y equals x. Okay. And numerically, pod 3.
Like if you had a table of values, the x and y values.
Okay. Pretty much no matter what, our x's and y's are switching, right? You remember that about inverses. Okay. If you remember back to Algebra 2, a couple years ago, but the formal definition, okay, yes, we switch x and y, that's how we find them. But in order for two functions to be inverses of each other, then both compositions turn out to be x. Okay, don't feel like you need to write down all of those words. But if we have an inverse function, then f composed with g equals x and g composed with f equals x. What does that mean? The functions undo each other, right? We talked about the other day the natural log of x and e to the x. When those are composed together, they cancel out and you're just left with what's inside. That's basically what I'm saying right here. Okay, when you have two functions that are inverses and they're composed together, they undo each other. Okay, the square root of x squared, x cubed to cubed root of x cubed. Okay, inverses undo each other. All right. Now, going back to what Table 2 said about graphs, all right, we know that if we have an inverse, then we have this reflective property about the line y equals x. What is important for you to know as we get into the calculus part of inverses, and you know this already, but if AB is on the graph, then BA is on F inverse. We're going to have to use that quite a bit as we're finding inverse derivatives. So make sure that that is something that you write down. If AB is on F, then BA is on F inverse. X and Y just switch when we go from inverse to function. last year in pre-calculus, at the beginning of the year, you talked about inverse functions. Okay? When you talked about inverse functions, you talked about something that helped you determine whether a function had an inverse. Okay, so let's just flash back to functions. How do we know if something is a function? We have a test. We have the vertical line test. Okay? We have the vertical line test to determine if we have a function. How do we determine if a function has an inverse? Take 30 seconds to brainstorm. See if you can remember back to last year.
Is that like real? Is that it? Really?
So Marcus was being funny saying horizontal line test and people laughed at it. So what's true? That's right. Yeah? Okay? Horizontal line test. Okay? If we were to take something like a parabola, that's a function, right? But if we draw a horizontal line through it, it crosses more than once. Okay? If this is a function, if we reflect this about y equals x, we would get this graph. Is that a function? It's not. And our inverse has to be a function, which is why the inverse doesn't exist over here. Okay? This doesn't pass the horizontal line test, so it does not have an inverse. Okay? However, if we had the function y equals x cubed, does that pass the horizontal line test? Okay. If we were to graph the inverse, right, reflect that graph about y equals x, we would get that, okay, which is a function. Okay. So a graph must pass the vertical line, the horizontal line test in order for the function to have an inverse. Now, let's talk about how we can prove that with calculus. When we say that a function passes both the vertical test because it's a function and the horizontal line test because it has an inverse, we gave it a special name. We only mentioned it briefly last year, so if you remember it, I'll be impressed. But does anybody remember what we call those functions? It's okay that you don't remember. All right, but maybe when I say it, you'll remember, or maybe not. Okay. If an inverse is if a function has an inverse, then we call it 1 to 1. There's 1x to 1y, 1y to 1x, because it passes both the vertical and horizontal line test. Now, if a function is 1 to 1, then we say that the function is monotonic on its domain. Write it down and I'll tell you what monotonic means. Okay? Okay, so our graph y equals x cubed, we consider to be monotonic because it is always increasing. Okay, I'm going to come back over here. This is monotonic, which means it has an inverse because it's always increasing. Okay, now what about a graph like y equals negative x cubed? Does negative x cubed have an inverse? Yes. It is also monotonic, but it's always decreasing. Would this graph right here have an inverse? No, because we switched from decreasing to increasing to decreasing. Okay, which is why we fail the horizontal line test. Okay, so we can actually use derivatives to determine whether we have an inverse or not by looking at, is our function always increasing or is our function always decreasing? Okay, now if I wanted to verify that our function was always increasing, what would need to be true about our derivative? Our derivative would need to always be positive. Okay? If our function was always decreasing, how would we know that? How would we know if our function was always decreasing? Okay, so what would the derivative look like?
Negative.
The derivative would always be negative. Now in the case of like x cubed and negative x cubed, it is okay if the derivative is 0 as long as it continues to be positive, positive, or negative, negative. Okay, it is okay if it hits 0. All right. But what I'm going to show you is instead of looking at the graph to determine if it passes the horizontal line test, we can use our derivative to help us figure out that information. Okay. So go ahead and write down this example. Okay. We could graph this. But let's just look at the calculus aspect of it. Our derivative. Caroline, what is it?
2x plus 2.
2x plus 2. Okay. 2x plus 2. Is it always greater than 0? No. It's greater than 0 when x is -1. But to the left of -1, that derivative is going to be negative. Okay? So, since our derivative is negative and positive, then f of x has no inverse. That's an and. So I like a terrible and sign. Graphically, if we look at the derivative, if that helps you, the derivative looks like this. So here our derivative's positive, here our derivative is negative, and so it is not monotonic. Okay? Without calculus, what do we know about the graph x squared plus 2x plus 1? What would that make? It makes a parabola, and we know that any parabola is not going to pass the horizontal line test. But that was just a simple example for you to see. Now, once we get into polynomials higher than degree 2, we could have something like x cubed that is always increasing, or we could have a cubic function that turns twice. Do you agree? Okay, we don't know. And so we're going to have to either graph it, we're going to do that, or we can use calculus to save us some time with graphing. So, does x cubed plus x plus 1 have an inverse? We know that a cubic function could have up to 2 terms, or could not have any terms. So, instead of graphing it, let's use some calculus. Our derivative. Okay, Chris, what would our derivative be? 3x squared plus 1. What do we know about 3x squared plus 1? It's a parabola that is always going to be positive, right? If we think about this derivative graph, we know that it's a parabola that is, narrow and up 1. That's always positive. So, since our derivative is always positive, then f of x has an inverse. And here's the next thing I want you to think about. You guys told me at the beginning of the class period that we would need to switch x and y and solve for y. If I gave you that function right there, how would you feel about switching x and y and solving for y? You'd be a little nervous. Okay, you would have x equals y cubed plus y plus 1. Right? Okay. Now, what we're going to go over today is we don't have to find the inverse function in order to find an inverse derivative at a value. Okay? So I'm going to show you the inverse derivative rule for when we're just looking at one point. Not the inverse derivative as a whole, but just as one portion. Okay? So, write down the rule. Just write it down. So first of all, you're going to know the function. What this is saying is that the inverse derivative is 1 over x derivative with the inverse plugged inside. Okay? Now, where the heck did this come from? I'm going to show you why this rule is what it is. You do not need to write it down. You do not need to be able to regurgitate it. But what I would do is I would put a big box and a star by that rule right there. Because you need to remember that rule. Alright, so why is this rule what it is? So what do we know about f composed with f inverse? What did I tell you? It equals x. Okay. So we know that to be true. So if we take the derivative with respect to x of f composed with f inverse, we know that that should be the same of the derivative with respect to x of x. Right? Okay, so we'll start on the easy side. Derivative of x. Okay. Now, over here, we have a composition. So if we have a composition, we take the derivative of the outside, leaving the inside alone, times chain rule derivative of the inside. I know it's kind of awkward to write, you know, the inverse derivative, like all these symbols in the superscript. But then what our goal is f inverse derivative, which is this right here. So if we want f inverse derivative, then we would divide this factor over f prime of f inverse. Okay? So that's why the rule is what it is. But all I need you to be able to do is remember it. Okay, so we're going to do some practice. Okay, ready? Okay, you guys are a little tired today, so I'm going to make you get up before we do this example. If you are the tallest or the shortest person, stand up at your pot. Marcus is taller.
Oh, it's pretty close. I think it's Brett.
I would say Allie. It doesn't matter. It doesn't matter. I just want somebody to. Okay? Alright. So find a new seat, tallest and shortest pod members. Take your notebook. Okay, when you get to your new seat, now you have a little bit of energy, go ahead and write down this example. Okay, so let's talk about what we need to do. In order to find f inverse derivative of 3, we need to follow our rule, which is 1 over f prime of f inverse of 3. Okay. So there are a couple things we need to find. We know we need to find the derivative of f. That's simple. And we know we need f inverse of 3. Okay? So let's first talk about f inverse of 3. How are we going to find, okay, so let me ask you this. If 3 is the x value for f inverse, that means 3 is what for f? It means it's a y value. Okay? So for f, then we're trying to figure out the x value for f, which will tell us the y value for f inverse of 3. Okay, so let's start there. We need to know when is 1/4 x cubed plus x minus 1 equal to 3. Okay, now sometimes we can solve with some algebra, sometimes we can solve by just playing around with some numbers, and I'm okay with that. Okay, x cubed plus x, that's not something that's really going to be fun for us to solve. So let's just think about some numbers. Okay, you guys are good with numbers. What number could we plug in for x? 2. Not 1, right? We don't want 1/4 plus 1 minus 1. But if we plugged in 2, we would have 8 times 1/4, which is plus 2 minus 1. That would give us 3. So when x is 2, y is 3. Okay, let me maybe write it like this. F of 2 equals 3. Which means f inverse of 3 equals 2. X and y switch from function to inverse. Right? Okay. So now over here, I can write that the inverse derivative of 3, what we need is 1 over f prime of 2. Because the inverse of 3 is 2. So now all we need is f prime of 2. Okay. All right, so let's talk about f prime. Tyler, what's f prime? Let's go up here. Here's f. What would the derivative be? What would the power of this x be? Yep, good. So 3/4 x squared plus 2. Excellent. Plus 2, plus 1. It says 1. I don't know why I said 2. So 3/4 x squared plus 1 is the derivative of f. If we plug in 2 to that derivative, what would we get? 4? So 1/4 is the inverse derivative of 3. Okay, let's just review what we just did. Okay, in order to determine what f inverse of 3 is, we had to figure out which x value gave us 3 in our function. Once we figured out that x is 2 gave us y of 3, we could determine that f inverse of 3 was 2 because x and y switch from function to inverse. Okay, so that's why we changed this inside to 2. Then we found the derivative of f with our simple power rule, and inside our derivative we plugged in 2. And that is how we got 1/4. Yes?
The first equal sign you drew is like absolutely perfect.
This one?
Yeah.
It is.
Yeah.
That is pretty cool. Thank you for pointing that out. And it's like, it looks typed, doesn't it?
Yeah.
You were hoping somebody would notice that too? Okay. You know what? I'll take a picture for proof that okay. Okay. Now that we half of us have a different view of the room, we're gonna switch it up again. If you are wearing red, blue, or green, find a new seat.
Hands count like normal.
We'll say shirt on your shirt. There you go, Ashley. Yep.
That's blue though. That's blue and that's red. Oh well.
What color are you not wearing? Okay, when you get to your new seat, I would like you to write down this example. Good idea. Those desks didn't get moved back very well. We'll fix that later. What makes this one nicer?
It gives you both.
It gives you the coordinate, right? Last time we only had the x value. This time we have the xy value. Okay? So, let's talk about what we want. We want f inverse derivative of 7, which is 1 over f prime of f inverse of 7. Okay, so let's just talk about one thing. If 7, 1 is on our inverse, we know that 1, 7 is on our function. We don't necessarily need that piece of information, but I just want to reiterate it for problems like what we did previously. Okay? So, let's just do this step by step here. The inverse derivative at 7. What do we know about f inverse of 7? It's 1. Okay. So what we need is we need the f derivative at 1, the function's derivative at 1. So, off to the side here, we're going to find the derivative. Okay? Marcus, what is the derivative of 7x cubed?
21x squared.
Good. Okay. The natural log of x, the quantity cubed. Trevor, help me out.
3 times the natural log x squared times 1.
Good, because we have to apply the chain rule. Very good. Okay. Don't worry about simplifying, because what do we need to do with our derivative? What? Plug in 1. Yes. Okay. So we need to plug in 1 to our derivative. What is the natural log of 1? 0, which means that's 0. F prime of 1 is 21. So our inverse derivative at 7 is 1 over 21. Okay, so this rule is a little bit different. Okay, it's not overly complicated, but we really have to get things figured out in our head since we're dealing with functions and inverses, right? We have all this flippy-flop going on, okay? So I can't stress enough how important practicing this in your homework is going to be, all right? What I'm going to do, I'm going to move you one more time, okay? So whoever has the longest hair and whoever has the shortest hair. We'll just say that you're like. You two, I would say you have shorter hair.
I technically have to
That is so old.
I do.
All right, good choice, CJ. All right, we have a great mixture now. Together at your new pod, I want you to do this. I want you to find the inverse derivative at 2, 0 for this function. I would appreciate if you collaborated. So I know you're writing it now, but then I don't want it to be quiet because I want you to work together.
Inverse.
Yeah.
Oh, yeah.
0 and then F prime. Wait, no, yeah, or 7. Plumbing and 2. Well, then we actually get 7 so that's 2 plus 7. And then after that, then it's
Yeah.
oh, yeah, right. Because we don't right.
That's 0. Yeah. So that's gonna be
You can put it on the smart board unless you feel more comfortable on the whiteboard.
ends up being 0.
Okay. Okay.
So that you get 1 over F prime.
Yeah, because the point was like, so you have 7
Thus make it 8.
So that's true.
Because like 4 people.
I feel like it's probably
It was, no, honestly, it was like,
Ask the best prompt. It's like the very small
time of
yeah,
this number.
Yeah.
So
Yeah.
under 10.
And it started like at that number, and then like 2 or 3 people dropped by the end of the year.
Yeah, so this would be 1. So this right here would be F prime of 0.
Since 0 is in the y.
Yeah.
Okay. What part are you? Okay.
I'm sorry.
Okay. 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 So, are you okay with like copying into this right here? Okay, so we need F inverse. Well, they gave us the point 2. So we plug 2 into the inverse to get 0. So, let me do the test. So from here, our F inverse equal 1 inverse 2, the y by
Oh, yeah.
So now in our denominator, Good. All right. So Callie's work is up here on the board. Do you agree with her work? Any questions for Callie or her group? Excellent. Okay. We have 7 minutes left of class. So at the pod that you're in, open one book and see if you can get through at least one problem, maybe even 2, before the bell rings. Okay?